É uma grande honra trazer o professor Castor Maple, da Universidade da Inglaterra. Ele trabalha dentro do Centro de Excelência de Cibersegurança na Universidade de Warwick. É com você, professor. Muito obrigado.
Thank you very much, Raphael. It's a real pleasure to be given the opportunity to speak to you all today. So, thank you very much. I'm going to talk to you today about current and emerging threats to vehicular systems. And this is work undertaken by myself and colleagues at WMG, at the University of Warwick, and also at the Alan Turing Institute. So I should say that some of this work is conducted, as I say, in collaboration with some colleagues. So the work that I'm going to present today is quite a range of work. Some of it will be some of the existing attacks on vehicular systems, but much of the work will be work that I've been lucky enough to be part of, working with groups such as ENISA, so the Cars and Roads Security Expert group of ENISA, working with Europol, the e-crime center, also with a number of people at Petras. Petras is the National Center of Excellence for Cybersecurity Research into the Internet of Things in the UK. I've been lucky to work with a whole bunch of organizations, including Jaguar Land Rover, Transport for West Midlands, Highways England, etc., on projects such as UK Site, Karma, and a bunch of others. And I'll try and tell you which project the work has come from. Also, the work is informed by discussions with the ZENSIC, Strategic Advisory Board in the UK. So ZENSIC is an organization that oversees the strategy for connected and autonomous vehicles in the UK. So on that advisory board, I sit with a number of people from government and from industry. And some of those thoughts have certainly shaped some of the work that I present. And finally, the Alan Turing Institute. So I'm a fellow at the Alan Turing Institute. It's the National Centre for Data Science and Artificial Intelligence in the UK. Some of the work that I'll present has been funded through that fellowship. Other parts of the work have been conducted at the Turing and in discussion with others. So they're all my acknowledgements before I start. So security and privacy in connected and autonomous vehicles, or any vehicles now, vehicular systems, is a particular challenge, and it's an interesting area for me. And we know that there have been a number of significant attacks over the years. Those attacks may have been lab-based attacks undertaken by researchers, or indeed real-life attacks in the wild. So I'm going to talk about a few of those, and this is by no means exhaustive, but some of the interesting attacks that there have been, before talking to you about how the system is evolving and what emerging attacks there may be, or challenges, and what kind of approaches I've been involved in it through these groups in trying to address those challenges. So, you know, quite some time ago, nearly 10 years ago, at the University of South Carolina, there's some work where what they did is they looked at attacking the tire pressure monitor on a vehicle. And what they did is, you can see here the application that they'd used. But essentially what they were doing is they were able to send fake signals. The tire pressure monitor is obviously Bluetooth connected into the vehicle. So what they managed to do is send some fake signals. So they used software-defined radio for the attack. And back in the day, this was about $1,500. That cost now has come down by an order of magnitude. So you're looking at $150 less for the equipment, the USRP equipment. And one of the things that they found was that the problem was twofold, really. There was no authentication. So you've got this system, and you're taking readings from the tires, to work out what kind of pressures in the tire. So you've got some sensors in there. And that messaging that was coming into the vehicle then from the tires had no authentication. And this is common in vehicles. We know the challenges of the controller area network bus, the CAN bus in a vehicular system does not have authentication, but this also didn't have, so this outside of the main vehicle, these messages coming in had no authentication, they had no input validation. So the warning lights, so when you've got tire pressure, the warning lights that come on that say that you've got low pressure in the tires only depend upon an alarm flag that's sent, not the real pressure in the tires. This kind of device, and especially now, it's very cheap. You can, when the experiments were conducted by University of South Carolina, Shu and his team, it was able to be managed from 38 meters away without any amplifier. As I say, not only are the cost of SDAs just so much cheaper now, the antenna used are really terrific, so you can get a lot of sophisticated attacks happening now. And what they also found, I should say, about this attack back in 2011 was that you could do it at speeds and between vehicles. And of course, you may think, well, is this really important? And that's one of the things that we consider about, how much security is needed in a vehicle. Well, I'm sure when it was designed, people thought, well, what's the kind of thing? Is it only a tire pressure monitor, so a tire pressure reading? And what's the harm in that? Well, of course, if you're getting, if you're a particularly high value target and you're getting told to pull over because there is a problem with your tires, that means that you may stop, and that could lead to other kinds of uncomfortable situations that you're in. I'm now going to talk about, many of you will not have heard about the attack on TPM or that specific attack, but I'm going to talk about two attacks that you definitely will have heard of, I'm sure. This is the first one, and this is Sami Kamkar. Of course, many of you may know of Sami. This is the OwnStar equipment. So it's a man-in-the-middle attack, and it was a vulnerability in the app that is used to track, unlock, and start GM vehicles. So Sami managed to apply this man-in-the-middle attack. And first of all, it was called OwnStar because it's a play on the OnStar app. But he adapted that attack so that he could actually compromise BMW vehicles, and then Mercedes and Chrysler, etc. So the way that this works is it was impersonating a familiar Wi-Fi network to trick the user's phone into silently connected. And this is what happened at the time. Your mobile phone has a set of connections that it's previously connected to. And what would happen is you'd have a Wi-Fi access point that would broadcast and say, I am a certain network, and it's one that you might have connected to before. So your phone goes, oh, okay, so I'll connect to that network. So what happens is you connect to that network, and it's not authenticated, the network. So what would happen is that rogue Wi-Fi access point could steal the credentials from the mobile phone through the remote link app, and then through a cellular connection send those credentials to the hacker. And using those credentials, Sami was able to show how you could track a car, you could unlock cars, you could start ignition. But because you've got access to effectively the app now, because it was the app password that was sent over the cellular network, you could access and change, in fact, the name, email, and some other personal information, and potentially something around credit cards. But of course, that's not something Sami would have done, but could happen. So that was a sort of man-in-the-middle attack. Sami's applied that kind of technique to lots of other areas, and it's very interesting, some of the work he's done. But it shows you that it's not just restricted to the vehicle, but this wider vehicle in some sense. And then this is a picture that many of you will have seen. It's going on 5 years now, and it's Miller and Valacek that at that time working with IO Active. What they did is they managed to compromise the Jeep. And what's interesting is there was a lot of cars affected, 1.4 million cars affected, and they could control the steering and braking. And if you look on YouTube, for example, you'll see the Wired video where the journalist is in a vehicle that's been compromised and they managed to steer and brake. But what's interesting is this kind of work that the guys had done, which was very, very good. I was a big fan of the work that they'd done. So they were researchers, so they weren't being malicious. But they'd shown the year before at Black Hat that actually they could take some control of a vehicle, but it required a local connection. So they were actually plugged into the ODB2 port of the vehicle with a computer and managed to take control of the vehicle. And I think at that time people thought, well, that's not too important because, you know, you will notice if somebody is sat right next to you in the vehicle with a laptop plugged into your car. Of course, they then managed to remove the need to be sat there by a compromise that utilized the way that the onboard unit was connected and how the infotainment unit was connected and how you could access the internet for the vehicle through the Sprint network. And that led to the remote attack that you'll see in that video. Some of the connected autonomous vehicles that we're seeing now and in future are going to have Lidar implemented. And there's some really good work. And I think Jonathan is still at Security Innovation Company that set up, but at the time was at University of Cork over in Ireland. And what he did is manage to do some Lidar spoofing. So it worked at a distance. And what it essentially does is sends Lidar signals so into the receiver. And actually what it can do is confuse any kind of autonomous features, because you can just spoof lots of obstructions in the way of the vehicle and send that into the Lidar unit, and that causes the vehicle to essentially have a false sense of the situation and most likely to cause it to stop. So you weren't actually taking control of anything else, but you were feeding false signals into the system. There are other attacks as well. So one particular attack that was quite interesting was an attack that was presented in IEEE transactions on ITS in 2015. And what that did is it used the fact that many people can interface with their vehicles through a smartphone. So they created a rogue app, so a malicious app. So the researchers were quite open about it, saying, look, it's not a great attack because, you know, it's a fake app, you know, but it's interesting. Well, I think it's really interesting the work that they did. They acquired this CAN data frame using a diagnostic tool. But the whole point was that they'd got an app on the on an app store that was compromised. So it's not necessarily the iOS app store, I should say, but it was an application store. And if you downloaded that app, it was a malicious app. So what it did is it effectively allowed them to get your credentials. So long as you used it once with the vehicle, they could then inject CAN data frames. So notwithstanding the fact that they said it was almost like a toy kind of attack because it was this malicious app, I think it's very important because people don't often know what is the correct app. We know that there have been apps that have got security weaknesses on open app stores, and they're doing a lot of work to try and combat that, but it's just very difficult sometimes to ensure that it isn't a rogue app that's available on the store. So I thought that was an interesting attack that was certainly valid. But one of the most interesting attacks that I talk about often is the attack that involves the American farmers. And this is really interesting because it shows the kind of threat actors being different to what people expect. And this is the fact that John Deere are tractors that are, or farm machinery that are made around the world, but very popular in America. But they are very expensive, and that's because they're very good machines. But what John Deere wanted to do is make sure that they didn't have people having unauthorized repairs. And the way that they did that is they effectively locked the system, so you could only go to a authorized John Deere dealership. Well, for some people in America, that was seen as too expensive, and it may be too far as well. So what a lot of farmers did, enough that it would cause a worry, is that they signed up to a paid-for invite-only forum on the internet. So it was very restricted. It was developed by some Ukrainians, and they downloaded some software which was like you might jailbreak your mobile phone, but this jailbreaked a heavy piece of machinery, so that now you could get an unauthorized person to look at your vehicle. Well, this is much worse than having your phone that's in some ways compromised, because now you're leaving yourself open to, how well do you know the Ukrainian developers of this system? You're paying for it. There's a real problem about the security, and this is really about the motivations. They're not just criminal gangs that might want to make some money, so financially motivated, not necessarily nation states, but American farmers wanted to hack their own tractors and then leaving them vulnerable as really heavy pieces of machinery. So there's some of the attacks that we've seen. And if we consider going forward, what's going to happen? Well, we're going to see more and more vehicles sort of cyber-enabled, so depending upon electronics, and connected and autonomous. So what we're seeing is the connected autonomous vehicles ecosystem becoming more prevalent and becoming increasingly complex. So we have one project at the University of Warwick in WMG, working with other partners, including University of Surrey, and working with Jaguar Land Rover in the UK. And what we're looking at is an architecture that is what we might call a three-tier architecture. So we are looking at this sort of collaborative autonomous system. So we've got the project called Karma, and what that has is a sort of cloud infrastructure that a vehicle can connect to, but through what we call the Karma Edge. So you've got an edge system that the Karma vehicle connects to. And what you've got is typically that vehicles will speak to one another through the edge system. Yeah, so you might have some limited vehicle-to-vehicle infrastructure, but really this Karma Edge is where there's a lot of intelligence at the edge. So what we're getting now is much more collaborative and cooperative vehicle systems. That leads to some really strong use cases, and we're currently developing those and running live trials as well as fundamental research at WMG. But also it leads to security challenges, and that's around challenges around security and privacy. So we've got some projects looking at the privacy, how we can actually, if you want to use this kind of system for platooning, for example, that's very cost effective and can lead to increased safety as well as financial efficiencies. The problem is you may have to give up a lot of personal information about where you're going, for example. So we're developing new techniques to keep that kind of information somewhat private, but at the same time highly effective. In another of our projects, what we did is we defined a cloud reference architecture. We defined a reference architecture for connected autonomous vehicles. And this is the part where you've got the cloud. So we define it in a sense where you've got communications and data storage and APIs and microservices. So you've got some cloud components. And you can see here, just like that Karma system, you've got this cloud part, you've got an edge part, and you've got vehicles. So you've got some vehicle to infrastructure communications. So we developed, working with a whole bunch of people from industry, this reference architecture. It's got a number of different aspects to it. So there's we define the whole architecture, and then each of the architectures for the vehicles, for the cloud, and for the edge. And what we can do from that is we can overlay onto that specific instantiations of services. And what it helps us do is, by doing this, we can see where are the communications. So you can see here in this edge reference architecture, you might have some communications between actuators and the environment and infrastructure. You might have a laptop plugged in. What this does, by having this visual representation, this reference architecture, it allows you to consider new services or approaches where what you do is you instantiate. So you put where the API is, you put your specific API, so you put some detail in there. For your service, you would actually visually and semantically connect the system through this architecture, in a sense. And what it allows you to do is to identify easily some of the threats that there might be. Such an architecture would help with, I mentioned before about Miller and Valicek. If in 2014, researchers have looked at the reference architecture and recognized that what the first attack was doing was getting into the controller area network through the OBD2 port. If they recognize, hang on, there is a connection to the OBD2 port through the infotainment system to cellular, they would have recognized that the attack surface was slightly larger than first anticipated, and therefore that was an attack vector. Identifying that would have prevented and could have led to some changes that would have prevented the remote attack that I talked about and showed you earlier. Within the Petras Center of Excellence, I lead some work on transport and mobility, and I just wanted to highlight here some of the challenges that we're seeing. So you can see here, location privacy was seen as important. So this is a word cloud talking about what was most important to people in an expert group around security for vehicles. And you see this physical and cyber coming together being the most important thing that people saw. But also, it's not just a technical problem, it's a socio-technical problem. And that human out of the loop was something that was picked up as important and worthy of looking at. So some of the challenges we've got, and some of these remain, we held the workshop a few years ago. There's work going on in this area, but still remain around public key infrastructure. So how do we make sure we've got effective public key infrastructure so that vehicles can communicate with infrastructure and each other in a trusted and secure manner? How do we manage the supply chain? How do we handle the dynamic nature? Because we've got vehicular ad hoc networks have been around for quite some time, but we're much beyond that as we move into the Internet of Vehicles. We don't even know what the edge of the vehicle is. It's certainly not that physical car or vehicle, because there are other devices that attach to it. Other kinds of work, and some great work going on in Europe at the moment around over-the-air updates. The trust in the over-the-air updates. The Fiat Chrysler, it was quite interesting. The update was either go to a dealership, or you could get sent a USB stick, you know, and that's not optimal. Over the air, you know, we know that Tesla does it very well, but it's still not known about how we manage that or indeed regulate it. One of the particular challenges that was of interest to the UK most recently, we looked at within the UK Site project. So the UK Site project is part of a 41-mile living laboratory around the Coventry area. And we took part in this program, and I'll tell you a little bit about one of the interesting things that we found out. But that living laboratory is now quite a large test bed, part of an ecosystem of test beds in the UK that's been overseen by Zensig, who I mentioned earlier. And this is part of now what we call Midlands Future Mobility. So that's one of 5 or 6 test beds within the UK for connecting autonomous vehicles. But what we did in that project, as well as lots of security elements, one of the things we looked at was jamming. And the reason to look at jamming is it's very cheap. So we looked at jamming technology. We bought a piece of kit for around £6, so about $8. It came from China within a week. And it was just a simple jamming device. There are very sophisticated devices, but this one was a very simple one. It managed to jam a lot of the signals. It didn't affect GLONASS, but that's just to do with the antenna and the range that it's working on. But you can see that Galileo and L1 GPS were affected. And this is something that is a worry to some people, but it's not insurmountable. But where the problem really arises is when you have some jamming. So we did some jamming within our Faraday case. So we've got a very good test facility in the university, and we did some intelligent jamming. And what we did with this intelligent jamming is we managed to jam in such a way that the jamming was not detected by the unit. And that's where the problem lies. If you don't detect that you are being jammed and you feed false information forward, that becomes a real challenge. And that's what we managed to do and rectify in the ADAS system that we were using. I also want to talk about a rather large project that we took part in recently. So it's large. It was a short funded project. It was run through Zensig, and it had a bunch of partners. So the core partners were Myra, a test proving ground in the UK, Thales, international company, and BT, and the University of Warwick, and Oxfordshire County Council, and CFMS. So they were the main partners with ASIN, sorry. And then we also managed to contract a number of very strong partners to help us, including 2 universities, the University of Bristol and Coventry. So this work was done with the Automotive Council. It was part of a feasibility suite that Zensig had commissioned on behalf of the government to look at a national centre of excellence for cybersecurity research in the UK. So we want to develop a strong facility. And as I say, there are 7 projects. WMG was involved in 3 of those 7, and this is just one of them that I'm mentioning. But I would advise people interested in this area to have a look. I'll talk briefly, because I haven't got much time left, I can see, about what we were trying to do in that area. But we were really talking about this connected vehicle infrastructure, and how can we ensure that we move from the current status, which really could lead us to some trouble in how we talk about security, because, you know, can we really guarantee the security of a vehicle? No, we can't say that. But what we need to do is make sure that what we're doing is we've got justifiable confidence that we're going to get a good outcome if there is a cyber attack that leads to compromising the system. So what we need to do is think that we're going to have emerging system failure, and how do we ensure that we are confident that we've reacted carefully. So it's not saying we've secured the vehicle, but what we're doing is making it resilient. And what we've really got to do is make sure that what we can do is we have a threat, And if that threat is realized, we need to make sure that we can detect, understand, and act on that threat before we hit catastrophic consequences. And those catastrophic consequences are consequences that are at scale. So they hit a number of vehicles in a significant manner. So depending on where we act, it may be that we don't detect the threat, we may not understand the threat, or we may not be able to mitigate the threat. So we need to detect, understand, and act within time. And what we want to do is make sure that we can shorten that timescale so that we have acted before catastrophic consequence. But also, as well as that, what we want to do is make sure that if we think about the number of units that are affected, we want to make sure that we don't have a significant number of units affected. So as well as increasing the time that we've got, that we've managed to act before catastrophic failure, we want to make sure that actually what we're doing is decreasing the number of operating units that have been affected. Okay, so the fewer that are affected, the better position we are. And finally, one thing that we would like to do in this methodology is to make sure that we appropriately adapt the system. So we have frequency by which we update the system, so that these updates happen in such a way that the knowledge that an attacker has gained becomes less useful because the system has changed. So we've used a number of techniques to do this. So what we're trying to do is, again, recognize that we cannot hit this 100% secure, but rather our probability of identifying the vulnerabilities is increased. So we're trying to push that curve up so that we detect better. Once we detect, we've got to make sure also that we're increasing our probability of understanding. So we've got some intelligence or some way to say, how do we understand how this is going to impact on the system? And finally, can we roll out action as quick as possible? And we're trying to do all of that before we hit catastrophe. So let's see there. If we want to reduce the impact on vehicles, what we really want to do is make sure that we've engineered what we're calling significant difference in the systems. So what we've got is a number of engineered differences, so that here you see half a dozen sort of levels. These are all differences, so that one can think of a class of vehicles or a set of vehicles in each of those. And that means that if there is a compromise of one class, it doesn't affect every single vehicle. And finally, those what we propose is we have these proactive updates, so that it means that the knowledge of the attacker cannot be as effective as it might have been. So what we've really got here is three principles. What we want to do is increase the probability of detection, understanding, and acting. We want to increase the number of engineered differences, and we want to invoke a continuum of proactive updates. And as we do this, we've got some arguments for certification, because certification is absolutely vital and still an ongoing problem, which we say, okay, we're going to certify around the probability of detecting those threats, the probability of understanding the threats, the rate at which mitigating actions can be deployed, and similar to things around the security, physical security of vehicles. What about the time for a threat to propagate? We're also going to look at the quantity of engineered differences and that frequency of proactive updates. So they become the factors by which we might certify a vehicle. Okay, I'm aware that I'm getting over time, so I'm going to rush on a little now. I should say all of this work can be found on Archive. I'm one of the authors, with some of the professors from Bristol University, some people from industry, but there's a whole host of people behind all of the work that we're talking about here. But what we want to do is make sure we've got calculations to look at the resilience of a system, so we can define operational resilience. So if a system is compromised and we want the performance metric to be at 100%, as it's compromised, what we want to do is build a resilient system so that for us, if we look at this dotted line, which is operational performance, so it's below optimal performance, but what you want to do is make sure that that operational loss is minimized, and that the system can recover, so one can see afterwards over time there's a recovery here. I think I'll leave talking about privacy for now, given the time, but I just want to make some summary comments, and they are, if we want to make sure that we want to combat the threats, we need to make sure that we work together. That's academics and industry. I'm proud that I do that a lot, and a lot of people that I work with in industry are like-minded. We need to think about physical and cyber, as well as the technical people and process aspects. And we need to think about that difficulty between fail-safe and fail-secure. When I say thinking like attackers, this is a rather old example that I give at the moment. I do like this. So there's a lost iPod Touch. So you can see how old this is. But it says $50 reward, much lower than the value of an iPod. So somebody's put lost iPod Touch, $51 reward, hoping to get hold of that iPod Touch. Well, that's the kind of thing that sometimes happens. Attackers will not think like us, and we need to think differently. If we just think within our own mindset, we're on a losing battle. So we need to think like attackers. We need to think about rational activity theory, for example, so cost-benefit analysis. So attack threat modeling is a pretty good way to say, how will somebody try to attack a system and how much effort will they put in? So one of the arguments can be that you decrease the value of an attack, and the engineered differences, for example, is one way to do that, because you may not be able to attack at scale if those engineered differences exist. So my final slide in summary is that the ecosystem is very complex, and attackers are often well coordinated. So therefore, we must coordinate in our fight against them. That means academics, it means industry, it means law enforcement. There are a number of attacks, an increasing number of attacks, and understanding these has to move from those researchers, the Miller and Valacheks, the Jonathan Pettit, the people like ourselves at the University of Warwick, and we have to make sure that that knowledge goes through to systems engineers. The challenge is non-trivial, but I really think by working together, it's certainly a challenge that we can meet. Thank you very much.